Hello everybody, in this lesson we're going to continue our studies of Unit 4, bonding, and we're going to focus today on ionic and covalent bonding. I've used this word in previous videos, ionic, but covalent, this will probably be your first day with that word. Let's get started. So while I don't have a bookwork associated with this lesson, I do have a quiz associated with this lesson. So you'll need to be studying all of the lessons since the beginning of the unit to get ready for this quiz. Remember, quizzes are worth a ton of points and you care about your grade, so do study. The aim today is what are ionic and covalent bonds. I want you to copy down this table, which will serve as our do now for class tomorrow. But what I want you to do for the next slide is that the next slide contains a video that I found on YouTube and wanted to share with you. So it's about 2 minutes long, so you do not have to take notes on it unless you're an overachiever. And you could just enjoy it, and it'll be a nice preview into ionic bonding.
We have previously learned about the formation of ions. Now we will learn about ionic bonds. Ions, as you already know, are formed from the loss or gain of electrons. Electrons, however, do not suddenly appear or disappear. They are in fact transferred from one atom to another. Let's look at sodium chloride as an example. Sodium loses one electron to form a sodium ion. The electron is not lost, but transferred to chlorine to form a chloride ion. So we have a sodium ion and a chloride ion. They are oppositely charged ions and will be electrostatically attracted to one another, much like how opposite poles of a magnet are attracted to one another. This electrostatic attraction is an ionic bond. Sodium chloride is an ionic compound because it is held intact by ionic bonds.
So let's get some notes in for ionic bonding. I hope you enjoyed that video. I'm sorry it was echoey, and I'll try and figure out how to stop that in the future. But what is an ionic bond? From the video, you probably picked up that it's a bond between typically a metal and a non-metal, and it's also a bond when electrons have been transferred from one atom to the other. And in terms of electronegativity and ionization energy, why do you think that non-metal atoms bond ionically with metal atoms? So first of all, non-metal atoms have a small radius. And since they have small radii, then that means that the non-metal atoms, I'm saying Nm, the non-metal atoms tend to have high electronegativity, and they also tend to have high ionization energy. Whereas the metal atoms, with their large radii, tend to have low electronegativity and low ionization energy. Therefore, in terms of electronegativity and ionization energy, why do you think that non-metal atoms bond ionically with metal atoms? It's actually quite simple. So since the non-metal atoms have a high electronegativity and a high desire for electrons, then that means that they're going to want the electrons that metals have. And metals actually have low electronegativity. They don't want to gain electrons. And more importantly, metals have a low ionization energy, which means that they will resist the loss of electrons very little. So it's those two things together, that non-metals want to gain electrons and that metals don't mind losing electrons, that you get ionic bonds, or a transfer of electrons. So I just said that the low ionization energy atom gives away electrons. All right, let's compare the electronegativities of lithium and fluorine. I just looked it up on my periodic table. lithium has a value of 1 for its electronegativity, which is pretty low, and fluorine has a value of 4 for its electronegativity, which is the absolute highest of all elements. So the question continues, if lithium and fluorine were bonded, how well would they share electrons? The answer is not well at all. Since fluorine wants to gain electrons very much and lithium is the opposite, then fluorine will end up taking electrons from lithium. And again, that's just because fluorine has a very high electronegativity and has a desire to gain electrons, and lithium has a very low electronegativity with a low desire to gain electrons. And so the electrons will be transferred from lithium to fluorine. So one reason why ionic bonds are considered to be weak bonds is because the elements that are involved in the bond have stable electron configurations after the electrons are transferred. So in an example of lithium versus fluorine, where lithium has 1 electron in its valence shell and fluorine is missing 1 electron in its valence shell, then what's going to happen is that lithium will transfer its electron to fluorine. This will make them both ions and it'll make them both stable. So I've shown them here on the other side of the arrow, both with brackets indicating stability, and lithium has no electrons around it where fluorine has 8, and they also have their charges. So these are my ions, and we can consider this bond in the space between the lithium and the fluoride ion. We can consider this bond weak because, well, in other words, if we were to take these 2 particles and separate them, it would be relatively easy to do because both of the elements have stable electron configurations and don't need to stay near each other to maintain that stability. On the other hand, the premise of the question that I asked is a little bit strange because, in truth, ionic bonds are not weak. It's just that some people consider them weak for this reason. But on the other hand, they're definitely strong as well, meaning that a +1 and a -1 will attract each other, and that attraction will keep them bonded. However, it's when you put it in a circumstance where, let's say, we dissolve it in water, which doesn't sound very drastic, but when you dissolve it in water, then these 2 ions will immediately separate. So there are ways to argue that it's a weak bond, and there are ways to argue that it's a strong bond. But if you're going to argue that it's strong, you should cite the attraction between positive and negative. And if you want to argue that it's weak, then you should say that when they're dissolved in water, they separate because they both have stable electron configurations. So lastly, it says, why is NaCl considered an ionic compound? In short, NaCl is considered an ionic compound because it has elements, sodium and chlorine, that are held together by ionic bonds. And the way I knew automatically that that bond would be ionic is because sodium is a metal, and therefore it has a low ionization energy, whereas chlorine is a nonmetal, and therefore it has a high electronegativity. And it's the interaction between the elements that have low ionization energies and high electronegativities that creates ionic bonding. In other words, whenever a metal bonds to a nonmetal, you always have an ionic bond. All right, so a covalent bond, this is probably the first time you've heard about this. So covalent has 2 roots. We have co and valent. So valent is definitely referring to the valence shell. And co is referring to this idea of sharing. So if you put that together, we have a shared valence shell. A covalent bond occurs when 2 nonmetal atoms with similar electronegativities share electrons. And the key word here is definitely share. So just like on the previous slide when we used the word transfer for ionic bonds, the key word for this kind of bonding is share. So in terms of electronegativity and ionization energy, why is it that non-metal atoms bond covalently? So the truth is, both of the non-metal atoms are going to be on the top right of the periodic table, and on the top right of the periodic table you have the highest ionization energies. And what that means is that neither one of the atoms is going to want to lose an electron. I guess properly we should say that it would take a lot of energy to remove an electron. That's what high ionization energy means. So if both of those atoms are going to resist the loss of an electron, then the best option, and they both want to gain an electron since they're on the top right and they have a high electronegativity. So we have high ionization energies and high electronegativities. So neither one of them wants to lose an electron, and both of them want to gain an electron. That's what high electronegativity means. So don't want to lose an electron, and they do want to gain an electron. And with that, the only solution is to share electrons. This can be related to electronegativity. So let's use table S to find the electronegativities of elements nitrogen and oxygen. So since these two electronegativities are very similar, we have a 3 for nitrogen and a 3.4 for oxygen, they're only 0.4 difference. We would say the electronegativity difference is 0.4. And 0.4 is a relatively small electronegativity difference. Since that is a small difference, I think that they would share okay, but not perfectly. So I just wrote down that they would unequally share electrons. Also this means that they would have a covalent bond. So since you have to share electrons when the electronegativity difference is low, then that also means that when the electronegativity difference is low, you have a covalent bond. So covalent bonds are considered very strong, even stronger than ionic bonds in many cases. Because, for instance, if you tried to dissolve a covalent substance in water, the bonds between the atoms won't break. And the reason for that is because when atoms are sharing electrons to fill their valence shells, then that means that unbonding would unfill their valence shells. So in other words, their valence shells are only full while they remain bonded. And that's going to lead to a very strong bond. So H2O, or the molecule for water, is considered a covalent compound for a couple of reasons. The first reason is that hydrogen is a nonmetal, and also oxygen is a nonmetal. And whenever you have two non-metal atoms bonding together, it's going to be covalent. There is another reason, however, and it has to do with electronegativities. Take a moment right now and look up the electronegativities of hydrogen and oxygen. And the electronegativity difference between these two elements, hydrogen 2.2, oxygen 3.4, is 1.2. While this electronegativity difference of 1.2 is significantly higher than the previous electronegativity difference of 0.4, we can still call this electronegativity difference low, and low electronegativity differences produce covalent bonds. So if you are extremely smart, and if you're one of my students, you are, if you are extremely smart, you're probably wondering, how do you make the decision, Mr. Wickline, between whether or not the electronegativity difference is high or if it's low? In New York State, we're not given any educational guidance on what is the difference between high and low, but I can tell you this. In other states, including the state where I went to high school, there is a cutoff point. And you can memorize it right now if you'd like, but it's not in your reference table because New York State doesn't support this idea. But the number is 1.7. This is the cutoff. So if your electronegativity difference is larger than 1.7, we say that your electronegativity difference is high and that you're ionic. If your electronegativity difference is less than 1.7, then we would say that it is low and that we would call your bond covalent. So we've reached the end of the lesson. I want you to copy down these 6 tables. One of them actually has the information in it to get us started, but copy down these 6 tables and we will complete these in class tomorrow. Also, don't forget this little question down here at the bottom. This is really important, this idea of ionic character, so I really want to have a chance to speak to you about it tomorrow. You also have this summary that I want you to copy down. The only thing that I would say that you can ignore for sure is what I'm putting behind this red box. So really just do the first 2 questions. Okay, thank you for watching. Make sure you have Cornell notes and a separate page with the do now, pair up, and summary. Have a wonderful day.